All right, we are wrapping up our course in forest ecology for fall 2020 quarter. For better or worse, usually it's for both better and worse. There are a few concepts that I think are appropriate for us to talk about here at the end of the class. What we're going to do is introduce some new things that attempt to pull all of the conceptual material of the class together and hopefully get you thinking about what's coming next in your education in forestry and in natural resources more broadly. So I'd like to begin this with a question that's probably on your minds, whether you are really focused on forests or if you're just broadly interested in the ecology of natural resources. And that's it. Are our California forest ecosystems resilient to current disturbance rates? If you care about these ecosystems, and I know that you do because you're taking this class, you probably want to know when and whether our forest systems are resilient to disturbance. The honest answer is we don't fully know. The environmental conditions are changing rapidly for many of the reasons that we've talked about so far. But we do know a few things about them. One is that they are becoming more oaky, and that we're seeing lots more mortality, substantially more mortality, measurably more mortality due to insects and pathogens. So what we're going to do in this vignette is examine some of the factors that help us understand the resiliency of these forests and why they are changing in these ways that we can measure. We're going to examine interactions between disturbance frequency and intensity, some modifications there. Look at the components of forests as complex systems and try to tackle what we mean by that. We're going to define silviculture, and hopefully I'm going to convince you that it's a good idea to practice and something that is worth getting better at. And then we're going to confront some definitions of simple, complex, and old forests that wraps all this together. All right, so let's dive right into it. Disturbance frequency versus impact. I'm sorry that my image is over the text there. That is impact. Just these two factors related to disturbance, and regardless of what we're talking about, fire, wind, insects, other factors, landslides or volcanoes, all of those things are disturbances. The frequency can alter the distribution of woody vegetation. And what's important here is that it can actually exclude woody vegetation. So if you're worried about how resilient California's forest ecosystems are, then it's important to understand how frequent these disturbances are and also how severe those disturbances are. Here's the point of this graphic. At high disturbance frequencies, it is much easier to shift the dominant vegetation from something that is woody, and in this figure, this is talking about shrubs, but it works for forests as well. It's much easier to shift ecosystems from ecosystem types that are dominated by woody plants to those that are herbaceous, grasses and forbs. Now, these three categories here, xeric, moderate, and mesic, are general, it's a general productivity gradient. And in dry ecosystems, frequent disturbance, in fact, even just a small increase in disturbance frequency can shift those systems from being dominated by woody plants to being dominated by non-woody plants. A great example are the deserts. If you clear a desert ecosystem, it will recover to woody vegetation dominance very slowly, if ever in your lifetime. These systems are just much more sensitive and less resilient. And on the other extreme here, mesic systems that have a lot of resources, a lot of water, a lot of nutrients, frequent disturbances will also those systems tend to be dominated by woody plants no matter what. great example of this is the eastern part of Puerto Rico, the Luquillo National Forest, frequently impacted by hurricanes, strong wind events that in some other setting could convert these forests from being forests to being dominated by herbaceous plants. That doesn't happen in Puerto Rico because it's so wet. These are very rich forests, very mesic, and they regrow as forests despite these regular and sometimes pretty intense disturbances. And then there's this middle ground where a lot of our California forests lie. There's variation in the productivity here, and because of that, there's variation in the degree that these forests are resilient. The last point that I want to make here is about the interaction between disturbance intensity and its frequency. And that's just to point out, I've mentioned this a couple of times at various points in the course, rare intense disturbances often I've implied this at least, that rare intense disturbances are less important evolutionarily. Forests tend not to be adapted to them because they are so uncommon. They don't, adaptations to those kinds of disturbances do not confer fitness because they are so rare. However, a regular low intensity disturbance is pressures systems to adapt to those. And so, oftentimes, our forests in California reflect the evolutionary pressure of fire, because it's frequent here and sometimes very intense. But in other parts of the world where fires are less common because it's so wet or some other factors, there's very few adaptations specifically to fire, if any. So moving on. California is very diverse, and we should ask whether succession differs across forest systems. It does and it doesn't. There are some aspects of forest systems that are common no matter what you're looking at. We see lots of different kinds of adaptations to the pressures of disturbance in California forests, and one I always like to point out here is resprouting, particularly in our coastal forests. Our coast live oak or bay laurel, really familiar species to us taking this class. Tree resprouting, very important for individual survival. Likewise, and this is common in other forest systems beyond coastal California, seedbanks and serotiny, particularly seedbanks, are very common. Serotiny, of course, is a kind of seedbank that's in the canopy. The survival of progeny, even if the adults die. The last thing that I want to point out here is that oftentimes, and in a landscape or an ecosystem that is shaped by disturbance, there will be different advantages for plants to be good at colonizing new areas compared to being good competitors once established in an area. So many plants, including trees, may be better adapted to colonizing disturbed areas, and they're able to get some competitive advantage for that. Other trees may come in later and are better competitors than these weedier species, these colonizing species. So what comes to mind there? Well, shade tolerance. Oftentimes, plants with high shade tolerance can establish underneath the canopy of something, one species or another that is able to establish quickly. Many different concepts in our class are coming together here, obviously. And the other thing to keep in mind, and I know I mentioned this at different times in our last topic, but this is dynamic. It's dynamic in time and space, and it can look like a real mess. But there are some things that are common among all of these systems, despite wherever they are in the successionary process. All right, so let's deal with some terminology here. Okay, forests as complex systems. Forests are complex systems even when they are simplified. They have characteristics of any kind of complex system, which is all manner of things, artificial intelligence, ecosystems in general, human societies. There are feedbacks in forests that tend to either amplify or dampen cycles within them. Negative feedbacks, tend to stabilize systems by suppressing anything that might potentially run away out of control. Positive feedbacks can do the opposite. So something that would say magnify inoculum of something that is pathogenic, a pathogenic organism. That would be a case of a positive feedback and might change how the system is working. A negative feedback could be something like tree resprouting. This is a mechanism for maintaining individuals within forests that may slow turnover of species within an ecosystem. There are many different kinds of examples here. Now, forests have many nonlinear relationships that are essential to how they work. Nonlinearities are harder to deal with than linearities, and they can produce some dynamics that are wholly predictable, but really strange and unexpected. Expect the unexpected with nonlinearities. And one of the things that happens was when you have a lot of feedbacks and nonlinearities, you can have emergence of processes or characteristics or states because of that. I like to point out island biogeography here because it's an emergent property that, that is driven by distances and the size of the habitat. And lastly, these forests are not static ecosystems. They are not static in space, they are not static in time, and they are not static in evolutionary time, which is much longer than we are typically accustomed to thinking about them in the course of a career or a lifetime. Okay, let's look at changes that we can measure a bit more easily. And this is where we're going to introduce the idea of silviculture. Now, silviculture is the art and science of growing trees, but it often means managing stands for some sort of desired outcome. Now, left to their own devices, many forest ecosystems have regular patterns of development. One of the easiest to understand is what's called even age stand development. And this is when a stand develops from a single cohort. This happens both naturally and in a contrived management sense. So let's say that you have clearcut, and then you replant and maybe even apply herbicides to suppress hardwoods so that you get a stand of timber like Douglas fir. What happens when left to its own devices, once you have established this pattern within the system, there are some phases of development that are very common. This happens among conifers, it happens among broadleaf trees, it happens even in shrubland communities to some degree. We typically have the stand initiation phase. You can imagine this as being low-lying vegetation, but the trees are there. In these conditions, light is not limiting. Nutrients and water maybe, but light is not. And then once we start to get light limitations, we start to have mortality in this phase called stem exclusion. And what's happening here is it means that there's not enough space, there's not enough resources for all of the stems in the stand. So some start to die. What is kind of interesting, and this, of course, is a depiction of a conifer stand that's easier to show here, and it's very common in conifer stands, is that once we start to get light limitations, we can actually get a reinitiation of understory trees. And I would argue that we can see this in many of the data sets that are available to us in this class. This phase here, the understory reinitiation phase, that's what it's called. But basically what's happening is we're getting some canopy gaps. Larger trees are dying at this point. That creates the adequate light environment on the understory to have regeneration. So this kind of stand structure is much more complex than either of these two over here. And what's great about it, if you're trying to grow timber, is that you can start to remove these trees, and then you have your next generation of timber species already established within your stand. That is a very helpful tool if your goals are to maintain timber. It also confers resiliency in forests because something can happen here. These trees can be killed by insects, they can be blown down in wind, and you have the basis for perpetuating your stand. Now, old growth, this is where sometimes I kind of run into some disagreement with how these models of development are put forward. Old growth, in this case, is depicting something that has more complex stand structure. There's more snags, there's bigger trees, there's trees in the intermediate stage, and also in the understory. It sort of is depicted here as having more biodiversity. The problem with this is my problem with this is that some of this structure can be achieved without the trees or the system being especially old. That's good in the sense that if you're trying to reestablish this kind of structure, it can be done. It can be done with careful management, and you don't even necessarily have to wait that long. I think that this kind of structure can be valuable, old growth structure, but true old growth forests take a long time to develop, and I think that they are best considered slightly differently than something that we might achieve in a lifetime or a career starting with this. Okay, so I want to talk about stand age distribution. Single age cohort stands. This is kind of one of the most simple classifications and kind of ways to talk about stands. It's also really valuable in terms of getting what you want out of stands. And imagining initiating from zero, say after a clear cut and herbiciding, or maybe a devastating fire or something like that. In certain systems, types of systems, especially when you have one species dominance because you contrive to make it that way, or it is that way naturally, when you have single species dominance, or you have dominance by a couple of species, but they're all kind of ecologically similar, you can tend to have this sort of stand development or stand structure. Oftentimes stands that are initiating from zero and have been managed to be this way, they will have a very narrow range of size class distribution. That's what you're seeing here. So this is just an estimate of the distribution of sizes. They're all clustered together in a single sort of stack here. What you would expect to find when you went out in the forest with this kind of distribution is this sort of structure. Everything's about the same size and height. What this does is it creates these kind of humps distributions, what's problematic about it potentially is when you have very few or no small trees, you don't have that resiliency that one would have in the stand exclusion, or in the understory reinitiation phase. Now, there are many things that can be done to deal with this problem, or there are many ways to create it, I should say, in the first place. If you're trying to grow lots of trees fast, this is effective. It is. It's effective. And you can do it by going out, thinning stands prior to what's called you can thin them with a technique called pre-commercial thinning. That's just saying that the material that's there isn't going to have market value, but by removing it, we can increase growth of the residual trees. There's also a technique called commercial thinning. This happens later. The trees are larger, and they may be, at that point, you may be able to sell them to the mill. It helps pay for these treatments. All of these things tend to narrow the size or age class distribution of trees. Sometimes that's not bad. That's not bad, even though these stands may be less resilient. So what's the example of that? Let's go to Vietnam. Here is in north of Vietnam. This is a single age, very simple system, timber management system. This is eucalyptus. These trees are grown in tissue culture and then planted out into these little bags, and then they're planted out into out into a particular site, and then they get harvested. The rotation is ridiculous, it's like 8 years, but this is the north of Vietnam. It's warm, it's tropical, it's wet, things grow fast, and a lot of the nation's domestic paper production is done with eucalyptus. They make it work, and that's great. It helps support the economy and make the economy more resilient. Now, there are some problems with this, and that's that these are very simple systems. They are accumulating a lot of pathogens, probably degrading soils, or require a lot of input, and the local communities here, they have really homogeneous economies. There's, this works for making a lot of timber, a lot of fiber fast, but it does have some other kinds of problems that really shouldn't be ignored. We have plenty of others, I can show you plenty of other examples of this kind of stand management. This is in the north of Maine, where I did my master's degree. And what's happened here, you have this, this is an old growth stand in the back. What you're seeing in the foreground was clear cut and then herbicided in order to regenerate the timber species here, which are balsam fir and red, white, or black spruce. Yeah, the silviculture works. You clear cut this, you herbicide to suppress the broadleaf species, and then you can go out and thin this pre-commercially, later commercially, and what you get are rapid rates of tree growth that conserve the local community by sending logs to the mills. That's why this was done. And that's what paper production in northern Maine is a very important to the local economy. Okay, so as I mentioned, this is not just something that happens in this kind of very contrived way, but it also happens in natural ecosystems. Bishop pine is one of the best examples. Bishop pine is adapted to regular intense fire. Regular, I mean on the course, the time scale of a few decades. What you end up getting are these extremely dense regeneration of stands. This is sort of a stem exclusion phase. It's amazing to me that these stands get so dense. And then they burn occasionally really hot. The stand burned this year, as so many places did. But I expect it to come back as bishop pine because this system is adapted to this kind of disturbance. It has a very large and resilient serotinous seed bank. It has seed bank in the form of serotinous cones. Okay, so let's talk about things that are more complex. Two things that I want to get to here, and that's point out, is that this is just the same silvicultural dynamics, just depicting more than one species. Many systems, most forest systems will follow these general kinds of patterns, but they do it as a more complex species mix. And if you give it enough time, you can end up with some things that are very complex here. Something else that is implied by this model is that we reach some final state. Now, you might have heard about this at some point, what might be considered, what was originally called climax conditions. This is an attractive idea that isn't always very helpful. When originally proposed, this suggested that systems were essentially evolved to reach some sort of perfect state, old growth. That is not always the case. Even our oldest stands, our truly oldest ecological communities are dynamic and they are changing over time. For example, the climax conditions would suggest that weedy species would be removed from stands at later stages, but that doesn't happen. And the reason it doesn't happen is that even in an old-growth forest, this is that stand in northern Maine that I showed, you have mortality. You have an opening of the canopy. You have potential for even weedier species to establish and persist within these stands. Look, there's hardwood broadleaf species in here. There's a whole bunch of regeneration. You can see that. Those are all trees in these, and there are different, there's a mix of species. So there's trees that are more or less shade tolerant in this system. The other thing that I want to do here is challenge you about your notion of what is an old system. Many old systems kind of fall under the category of old growth. And I think that old growth in some respects is even kind of a misleading term. Systems can reach a kind of stability that is, dynamic, kind of alluded to that. But they can also be simply late seral. That means they have structure, species composition, and things that we might care about that are associated with stands that have been around for a long time in some broad kind of set of conditions. Here's an example from Central America. It's from Chiapas. This is a system that, yes, it does burn occasionally, but it is a forest that has been managed by local people for a long period of time. And even if there are no old trees per se within the system, one could argue that the system itself is relatively old, and even that it may reflect the structure that one would expect should this forest have been, it reflects the structure of an old forest in this particular environment. All right, so we're going long here, but stick with me. Stand dynamics is not always a perfect lens to see the world's forests. Succession is weird sometimes, and we've talked a lot about the how differences in precipitation and timing of precipitation and so forth influence forest versus grassland dominance. Succession oftentimes can be mediated by many different things, and it is dynamic in space. So these models of stand development can be really powerful, but they can be kind of not just misleading, but kind of that kind of tempt you into thinking that you understand everything about the world, when that is not always necessarily the case. You get surprised by all kinds of different processes. Here's another problem here. Sorry, I'm cutting this off, but disturbances are often uneven or patchy. They occur at random times, but they can overlap. They can co-occur and potentially interact. For example, this is a photograph of the Needles area. We go to there in normal times during this class. You can see the extensive amount of mortality that happened from insect outbreak in the last year. And oh yeah, this thing burned this year. So you have a co-occurring and overlapping disturbance, and that potentially changes the intensity of the disturbance, and we don't know what that means for the resiliency of these forests. Straight answer, we don't know, right? But we probably should find out. And I say that because we know disturbance does not occur in a vacuum. We know that history matters for forest structure. And in fact, I can point you to different examples. This one's from John Stone, a paper published in 2016. Point to you examples of where overlapping or interacting disturbances matter. Last topic, last slide, last everything. Here is an example. This is from northern Minnesota. This is jack pine, a species that's well adapted to fire. Fire tends to favor jack pine. That's what you're seeing here. And a fire in this stand, and what you're getting afterwards is this species. Now, fire is not the only disturbance that happens in northern Minnesota. In fact, you're getting into the part of the world where wind disturbances can be more frequent and important. And wind is different than fire. It doesn't burn up the organic matter, doesn't scarify the soil, doesn't a lot of things don't happen in wind that do happen in disturbance. And the result is if you have a wind event, you tend to have dominance of spruce and fir, like you would in northern Maine. Northern Maine doesn't burn very often. Every 1,000 years, 2,000 years, 5,000 years, I can't remember. It's just so long, it doesn't really matter. But these species do occur there, and they will respond to different changes in canopy light, understory light levels. And then lastly, what happens here in these systems is you can have co-occurrence of wind and fire. What do you get then? Well, something kind of unexpected. Broadleaf species. Birch, which is really weedy, presumably establishing here because the fire intensity is much greater than would be normally expected in the jack pine scenario. So disturbance frequencies, disturbance interactions of disturbances and how they change the intensity of those disturbances and the outcome or the implications of that ecologically are something that those are questions that are right on the forefront of forest ecology today. Things that we don't know the answer to, but because they are more and more frequently happening in our forests, insect-caused mortality, occurring with drought, occurring with fire, for example, it's becoming more and more important that we understand that.